Excuse me, sir. Sir, we can't hear you, sir. You're muted.
Sir, you're muted.
Sir, actually, you're muted actually.
I don't think he's muted because if he was, he would have been showing the sign here. Probably some issue with the mic.
संचेत इतना स्मार्ट कब से हो गया?
Okay, so I think there was both the speaker as well as the microphone was set to some default option, and that's why we could not, yeah, you could not hear this. Okay, so what I was saying is we are interested in finding the PDF of the function of random variable in some easier way, and that's where the method of transform is useful. But that to do that, we need the function to be differentiable, and it should be strictly increasing. Okay, and if that is the case, then we can write the PDF of the random variable y as follows. Okay, so this is something we also discussed in the last class, and our goal is now to complete the proof of this. Okay, so we have to arrive at this formula. Okay, so let us do the proof of the method of transform, and this is for the strictly increasing case. Okay, we are assuming that the function is strictly increasing. So since g is strictly increasing, g inverse is well defined, right? So since g is strictly increasing, so we have done this. So I will go through this rather quickly. Okay, since g is strictly increasing, this implies g inverse is well defined. Okay, in other words, that is g is 1 1 and on 2, and this also implies g inverse exists. Okay, so these are the requirements for g inverse to exist. Now for each y in the range of x, there will exist a unique x1 because of the onto property of this. So for each y in range of x, there exists a unique x1. Okay, such that the existence of x1 is guaranteed by onto, and uniqueness is guaranteed by 1 1. So such that gx1 is y. In other words, that is, we can write x1 is g inverse of y. Okay, so this is what we can write, and our goal is now to find the PDF. Okay, so PDF of y. Okay, so this is the formula that we want to derive, or in other words, we want to prove the method of transform. So first we start with CDF. So FYY is probability that y is less than equal to y. Okay, this is probability that y was g of x. So this is g of x is less than equal to y. And this is probability that now, since this is a monotonically increasing function, it must be that x is less than, right, x is less than g inverse y, right, less than or like less than equal to. Okay, so this is happening because g is a increasing function. So I described this in the last class, so you can watch that video if you have doubt here. And this will be this is nothing but, since now you change this to a random variable x, now this you can write this as CDF of x. So CDF of x is capital Fx, and then this is the parameter will be g inverse of y. Okay. Okay, so this is what we have, and to find the PDF, what do? We differentiate the CDF. Okay, so we will differentiate the CDF. So to find PDF of y, okay, we differentiate. So we differentiate, and if we do that, then we get small f y, which is denotes the PDF. So this is d by dy. Okay, we differentiate with respect to y of fx and of fxy. Okay, so we will different. So the point is like the point is like f. So we have to differentiate y basically, but y is this, right? So I can do this additional step. Okay, so first step. So this is like fy. Y we want to differentiate. So this is d by dy of fyy. From here we wrote in terms of this, right? In other words, in terms of fx x1. Okay, so I can write in first this form. So fyy is fx g inverse y, and for a short form we can write x1, in the case of g inverse y. So d by dy of fx, and let us say this was like x1. Okay, so let us say this is our star. So from star. Okay, and I mean, this is like a temporary replacement just to keep it compact. So now if we do this, then what do we have? We have derivative of this, right? So derivative of this x1. Remember that this is function of y, right? Eventually this is g inverse y, and this is, so this derivative is with respect to y. Okay, and then what we have, because the chain rule applies, because x1 okay, so if that is the case, then because we see this as a chain, right? So this derivative will be with respect to x, actually x1. Okay, because I see this as a function of x1, and x1 is a function of y. Okay, so the chain rule, recall the chain rule. Chain rule is g of f of x. Okay, so let us say this is y, then dy by dx is dg by df times df by dx. Okay, so this is what is happening here. So f of g inverse of y, so it's like two functions there. So first df by dx1 and dx1 by dy. Okay, so this is so if we differentiate if we differentiate this as a function of as a function, so if it because this is like a PDF of x, right? So it will become a PDF because this is CDF of this is a CDF of x, and if I'm taking a derivative, okay, if I taking the derivative, then it will become a PDF of x. So this will be fx and then x1, and then dx1 by dy we keep it like this. Okay, so but dx1 by dy is nothing but g prime. Okay, so it's like dx I mean dy by dx1. So from here I can also write dy by dx1 is g prime x1. Okay, so we put this thing here. So fx x1 times 1 divided by, because this is dy by dx1, so we have to do 1 by dy by dx1. So this is 1 by g prime of x1. Okay, so actually this is what we have, and this is what we were supposed to prove. Okay, so this is the proof that we had. Okay, and additionally what we have is that here we have to say what was x1. So this is the x1 for which gx1 is y. Okay, so this whole thing now, so this is fyy. So this is what we were supposed to prove. Okay, so this is what we were supposed to prove. So this is the increasing case. Now the same thing will hold for the decreasing case. So let us see for the decreasing case. So let x be a continuous random variable, g from R to R be strictly okay. So for strictly decreasing, I have not like explicitly written down, but I think I can put some remark for strictly decreasing, and that should be like obvious. Okay, so in the strictly decreasing case, let us work out and write the result at the end directly. Okay, so for strictly decreasing, so let us start again with the PDF. So fyy is p of y less than equal to y, and this is, so y is g of x, right? So g of x is less than equal to y. So this is, so how can I change this to I mean this is strictly decreasing now, right? G is strictly decreasing. Okay, so now g is strictly decreasing. So note, now g is strictly decreasing, right? That's the decreasing case. So if g is strictly decreasing, right? If g is strictly decreasing, then how can I interpret this in, how can I solve for x, right? So this is probability that, so what will be there? In the increasing case, we had x less than equal to g inverse y. And in the decreasing case, we will have the opposite, right? So we will have like x like greater than equal to g inverse y, right? So in the strictly decreasing case, because g is strictly decreasing, right? So this is what? This is 1 minus, so I can change this to less than equal to by using 1 minus p, and x is less than equal to g inverse y. Okay, so this is like 1 minus x is less than g inverse y. Okay, so and this this is 1 minus, because I wanted to change this to like PDF, sorry, CDF. Okay, so that's why CDF is always defined for less than equal to, and I wanted a x here, that's why I solved for x and so on. So this is like now CDF of x and g inverse y. Okay, so to find PDF, we differentiate the above. So if we differentiate, then we get small y, sorry, small f, So this is d by dy. So it follows like before, fyy. This is, now what will happen in this case, right? So so this is so fyy is this, right? So this is like d by dy of 1 minus, so I just copy it from here, right? So fx g inverse y. Okay, so this is from here. Okay, so if I do a d by dy over this, there is a negative sign here right now. So this is negative will come out. Okay, and constant, there is no dependence on y, so this will be 0. So eventually this will be d by dy of fx g inverse y. So that's the thing. And similar to before, g inverse y is x1. Okay, so since so g of x1 is y, so this condition remains as like in the increasing case. So since gx1 is y, so g inverse y is x1. So this implies x1 is g inverse y, and here also inverse is properly defined because so g inverse exists because g is monotonically decreasing. That is, g is 1 1 and on 2 again. Okay, in that monotonically decreasing case also. So that inverse is well defined. So this becomes, so this is equal to minus d by dy of fx and x1, right? And so so like before, this will be by the chain rule, this will be f prime x x1, and then dx1 by dy, and there is a negative sign that we keep copying. So dx1 by dy. So this is equal to minus, so this is the PDF now. So fx x1 and 1 by dy by dx1. I've just written this guy like this, 1 by, because 1 by, so from here like dy by dx1 is g prime. So I can substitute that x1, and then it's dy by dx1 is g prime x1. Okay, so dy by, so the important thing to note here is what will be the sign of dy by dx1, right? So what will be the sign of the dy by dx1? Dy by dx1 is going to be negative, right? Because it's a monotonically decreasing function, right? So it is as if it's the negative of the of the usual derivative, right? So it's the negative, because when we are taking derivative, then it's like we are assuming that x is like going on the right and so on, right? So it's like this way we are talking about, right? And so our direction is this way, right? So our direction is this way. So if the function is decreasing, right? So the derivative is monotonically decreasing. So derivative as x increases, it's negative, right? And on the other hand, for positive, as we go this way, then derivative is increasing, right? So we know that the derivative is going to be negative in our case, in this case. Okay, so here so dx1, so dy by dx1. Okay, so dy by dx1 is g prime x1. Okay, and it's negative for for increasing values of x1. Okay, so what we will get here is a negative, or another way to say is like if I had gone in this way, right? If I have reversed my interval, if I go this way, then the derivative would have been like positive. Okay, so if I go in this way, then this way the function is increasing, and then this would have been just g prime x1. But since I am going this way now, but it's increasing. Okay, so in that case, this will be like negative. Okay, so if we will work out this for a strictly decreasing function, then it will make sense to put this in the following form. Okay, so this is like fx x1, and then modulus I put here, and g prime x1. Okay, so this is how I will try to observe the negative part. Okay, so I will illustrate this with an example of the decreasing case, why I will put a mod here. Okay, and I can do this for monotonically increasing, decreasing, like any one. Okay, so it has to be just monotonic. Then so it's like monotonic increasing or decreasing. So this is like monotonic decreasing case. That's what I said, and I have to put a mod here. Okay, that's because with the increasing values of x, my derivative is going to decrease here. Okay, and for okay, 1 second. So this is the case where it's a decreasing case, right? So let us work out some example, and then we will appreciate this. So this is the function fx. The PDF is given, which is fx, and this is 4x cube, and x greater than 0, less than equal to 1, and 0 otherwise. And y is a decreasing function of x, and we want to find the PDF of y. Okay, x is given, and we want to find it for y. So let us apply the method of transform here. So first of all, what is range of y? Okay, and in fact, what is first of all, what is like range of x? So range of x is what? 0 and 1. Okay, so 0 is like open, so let us put it open, and 1. But range of y, so y is 1 over x, so the range of y is 1, and so because 1 is included, and then infinity. Okay, so this is the range of y, and here g of x, which is 1 over x, is strictly decreasing. And obviously it's differentiable because it's 1 over x. Okay, so it's differentiable in it's differentiable yeah, so it's differentiable in 0 1, is differentiable in 0 1 interval. So like 0 is like open. Okay, so 0 1 and so, and what is the derivative of g? So we have the derivative of g prime of x is minus 1 by x square. Okay, so this is what we have. Now for any y in 1 comma infinity, for y in the closed 1 infinity, we have to solve for this inverse. We have to solve for the like x1, right? So what was x1? X1 was g inverse y in our case, right? So x1 is g inverse y. Okay, so if x1 is g inverse y, then this is 1 over y. Okay, so this is 1 over I, and for y in in closed one infinity. Yeah, so I have already written y closed one over infinity. Okay, so now I will differentiate the. Now I will apply the formula basically. Okay, so I will just apply the formula. So fyy was what? Fx x1 by g prime x1, right? So this is so PDF of x, and I substitute it by x1 here, right? So this is like 4x1 cube divided by, and since this is a monotonically decreasing function, okay, so for a monotonically decreasing function, I need to put the mod here, and if I put the mod here, then this is -1 by, and this is x1 squared is from here, and then I put a absolute value, and so so the reason why so this is a decreasing function. This is why I got the derivative to be negative. Okay, in this interval, in 0, 1 interval, my derivative is negative. Okay, so and here so after calculating all this, what we have is 4x1 to the 5, right? So this is so x1 is 1 by y, right? So this is like 4 by y to the 5. Okay, so this is the PDF of y that we wanted to compute. So to summarize fyy is 4 by y to the 5. For y, range of y is greater than equal to 1, right? So y is greater than equal to 1, and otherwise it's 0. Okay, that's according to the method of transformation. Okay, so now let us see this graphically. So y is 1 over x, right? So what is the graph of 1 over x, right? And x is lying between 0 and 1, right? So this is like a strictly decreasing. Okay, so this is like 0, and yeah, so the 1 will be like I mean, what I have drawn is the so what I've done is the is g of x, right? So g of x is like 1 over x. Okay, so this is a strictly decreasing function. Okay, so this is a strictly decreasing function in 1 and infinity. Okay, 1 up to infinity. Okay, so the derivative I will take, obviously it's going to be negative for all x, and since this is a monotonically decreasing, then inverse exists, and inverse is 1 over y. Okay, so the is 1 over y, and what else? What else? So so that's the application of method of transform for the decreasing function. And we can do this both for in the case where it's actually increasing and decreasing both. Okay, because there the rule will be to partition my domain into increasing and decreasing cases. Okay, so here is the case where I can have both increasing and decreasing. Okay, so here if I see from here to here, it's an increasing function. From here to here, it's a decreasing function, and from onwards, it's an increasing function. So here I will apply the method of transform for the increasing. Here I will apply method of transform for the decreasing, and here I will apply method of transform for the increasing. So I will find the inverse function of this in this domain, and then I will find inverse function of this in this domain, and then in this domain, and then I will add this up. Okay, so it's like piecewise I will I will add this. So hence, and this is how I will get the PDF. So in the case where I have a piecewise, not piecewise continuous, but I mean piecewise monotonous. By piecewise monotonous, I mean from here to here. Okay, so piecewise it's increasing and decreasing and increasing and so on. Okay, so it's a continuous random variable, and y is g of x, and we can partition the range of x into finite number of intervals such that gx is strictly monotone and differentiable on each partition. Okay, that's what I said here. Then PDF in that case will be given by the. So you break your problem into partitions, and then you find a PDF in a localized way, and then you add them up. So this is what I've written here. Okay, so to see, yeah, so x1, x2, xn are like the solutions of these. Okay, in other words, like you have to find the inverse function for each of these intervals. Okay, so from here to here you have to find the inverse function, from here to here you have to find the inverse function, and so on. Okay, so okay, so here I have an example of the case where it's increasing as well as decreasing. So this is a parabola. Okay, so y is equal to x square. So find the PDF of y. So this is the PDF of x that is given to me, and function of a random variable is given where its y is g of x, which is x square in this case. Then find the PDF of y, right? So does this satisfy the criteria of applying method of transformation? So let us check if is x a continuous and differentiable? Okay, so is x continuous and differentiable? Yes. So this is continuous and differentiable. So exponential of any variable is like, it's like continuous and differentiable, like any in the sense like some polynomial power. Okay, so that satisfies the continuity and differentiability, and can we partition the range of x into intervals such that gx is monotone? Okay, so can we partition such that gx is monotone in these intervals? Okay, so by gx I mean this one. Okay, so can we partition this, and on which intervals gx is monotone? Okay, so let us see a solution to this. So what we have is g of x. So remember that fx is defined for all x in R. Okay, so this is like the range of x is like all of R. Okay, so in this case the range of x is all of R, but we have to find range of y. So range of x is all of R. Range of y, since we have x square involved, so if you square the real numbers, you will be left with 0 and minus infinity. Okay, so the range of y will be 0 to minus infinity, and I'm sorry. Let's see. I'm sorry. What I'm doing here. So range of y will be like 0 to infinity basically. Okay, so because it's the square of these, right? Okay, so now what about g of x? Okay, so g of what is the nature of g of x for the values of x? So let us plot this and see. So this is a parabola. Okay, so for 0 to infinity, what is g of x? Is it increasing or decreasing, right? So 0 to infinity, g of x is increasing, and minus infinity to 0, it's decreasing. So we have like two partitions of our domain. So gx, which is x square, is strictly decreasing on 0 minus infinity, and strictly increasing on 0 infinity. Okay, so that's the observation that we made. We have to partition our domain and then we have to find the inverse function in each of the domain. Okay, so and we also note that derivative of g is 2x. Okay, so that's the, so now we will apply the method of transform. So recall the method of transform tells us fyy will be sum of fx xi by g prime xi mod, okay, I equal 1 to n, and this is another way to say was fx xi, and this was nothing but dxi by dy. Okay, I equal 1 to n. So for any y, so the range of y is like 0 and infinity, right? In this, what are the like the solutions for y is equal to g of x, right? So for any y in 0 infinity, we have two solutions for y equals to g of x. Okay, what are those solutions? We have two solutions. For, remember, we have to do solutions for this y equals to g of x. I mean just x. Okay, so those solutions will give us however many solutions are there, they will give us x1, x2, x3, and so on, right? So if we solve for this, right, so y equals to g of x. So what do we get, right? In other words, y is equal to x square. Okay, so what are the solutions for this? Method of transform requires solutions for this. So this tells us, remember, so we want to find the inverse, but inverse doesn't exist as a whole. If I take minus infinity to infinity, then inverse function won't exist because this is not 1 1. Okay, although this is on 2, this is not 1 1, and if I take inverse, there will be a conflict that I will have 2 points and for which I have the same one thing, right, pre-image. So that will create an issue. That's why we partition our domain in two parts, so that we will have the inverse function defined here. Okay, so for y between 0 and infinity, we have two solutions for this. And what are those solutions? So we have x1 is square root of y and x2 is minus square root of y. Okay, so if we solve for this, then these are the these are the solutions we are going to get, square root of y and minus square root of y. And okay, and now we can use the method of transform formula, right? So we have found x1 and we have found x2, and so if we apply the method of transform, so and then this will be fx x1. Okay, so this is fx x1 divided by g prime x1 plus fx x2 divided by g prime x2. Okay, so this will be fx1, right? So this is so the PDF, if you recall the PDF, this was 1 by square root of 2 pi x and e to the minus x square by 2 and so on, right? So this is so let me do one more step. So x1 is square root of y. So this is square root of y divided by g prime. Okay, so g prime of x1, right? So So g prime of x1 is what? It's like 2x. Right, so g prime is 2x, right? And x is square root of y. So this will be okay. So I can write this directly as, so g prime is 2x and x1 is square root of y. So this is like 2 times square root of y. And then similarly here, I can write fx minus square root of y, because x2 is minus square root of y, right? So then I have minus, so there will be mod here, right? So minus 2 square root of y. Okay. So if we combine this, so if we combine this, then what do we get? Right. So if we combine this, then what we will get in the end is 1 by square root of 2 pi y, because of this PDF you substitute PDF, and in place of x you put square root of. So there was this thing, right? 1 by 2 pi y, and there will be a 2 from here, and then I think not 2 pi y, but like 2 pi was there. Okay, and then there is a square root of y, so y goes inside the square root, so that's why I have clubbed everything here. And then this was e to the minus x square by 2. So in place of x I have square root y, so this will become minus y by 2. Okay, and same thing here, 1 by 2 square root 2 pi y, and e to the minus y by 2. Okay, so this is e to the minus y by 2. So there is half here, half here. So together if we combine, then this will be 1 by square root. Okay, so here I can write. So this is like f y is 1 by square root 2 pi y e to the minus y by 2. Okay, so and the range of y was indeed 0 to infinity. So this is the PDF of y using method of transformation. Okay, so if you remember this formula, then you can quickly plug in the values. The only thing you have to define is like where it's increasing and where it's decreasing. And increasing decreasing is needed because we have to find the inverse function here. Okay, so locally at least we can find the inverse function. If we do the inverse, and then we have to build the PDF piecewise. So we have to sum up the PDF. So from here to here it's defined, and from here to here locally the inverse is defined, and then we will glue them together by adding them. Okay, and then it will be defined for all of the range of y. Okay, so that's how we compute the PDF. Okay, so there will be few more questions. So I cannot go for the solved problem now. So I have a few solved problems where we will practice more on the method of transformation, especially the general case where it's increasing and decreasing both. So I will try to do more practice on this. Okay, and then we will go to special distributions. Okay, in case you have doubt, then you should always ask by turning on the microphone. Okay, I think I can listen to you. Okay, so okay then, so I guess that will be all for today. Okay, and the grades will be submitted in a couple of minutes. Okay, so okay, thanks. Yeah, have a nice day. Bye.